We talked about inductive reasoning, going from many specific cases to coming up with a general statement. The opposite of that is what we call deductive reasoning. Right? So once you form a hypothesis, once you have proposed a tentative answer to your questions, researcher will use deductive reasoning to test it. So deductive reasoning flows from general to specific. Again, opposite to inductive reasoning, right? So here's an example. Inductive reasoning would be all organisms are made of cells. Whereas deductive reasoning would be if all organisms are made of cells, and if ant is a living organism, then an ant will also consists of cells, right? So you're going from a general statement to our specific example of that general statement. So here is the scientific method, all the steps involved in it. Right? There's observation, there's questions and hypothesis, which is basically what we've been talking about. And then once you have a hypothesis, we are going to predict the results of an experiment that we are going to be conducting to test the hypothesis, and based on the results of the actual experiment, we are going to make a conclusion that would either support your hypothesis or it would refute your hypothesis. So these are the 6 steps of the scientific methods, and we're going to do some examples of go through some examples of these in the next few slides. So here is a very simple example of scientific methods. We do this all the time. We just probably wouldn't be thinking about the word scientific methods when we're doing it. Let's say your remote control does not work. Right? So that's the observation. The remote doesn't work. Right? So the instinctive question you would ask is, why is it not working? What's wrong with it? Right? And there could be, many reasons. Maybe it's broken. Maybe the batteries are dead. Maybe the on/off button is loose. Right? We don't know what it is. Right? So we try to come up with a possible explanation for this. And based on your experience, it's probably the battery. So the hypothesis, the tentative answer to your question of what's wrong, would be the batteries are dead. Right? So now you predict what will happen. With new batteries, it will work, right? And this is actually an example of deductive reasoning. So deduction usually takes place in the form of predictions about an experiment, right? So in this specific case, the general statement would be electronics runs on batteries, and without the batteries they don't work. That's a general statement. And since the remote control is an electronic device and it's not working right now, so replacing the batteries in it should fix the problem. Right? So that's your prediction. Then you go on and do your experiment. You've replaced the batteries, and one of two things can happen. Either the remote starts working, that means you were right, and so you fix the problem. And if the changing the battery does not work, then that means your hypothesis was wrong, and you will have to revise your hypothesis and start again in this process. So here is a very simple, straightforward example of how scientific method looks like. Right? Of course, it's much more complicated when you're doing actual experiments, but in a nutshell, that's basically what it is. So hypothesis, right? How do we come up with these hypotheses? Right? For the remote control is relatively straightforward, but in real life examples, in a lab, for example, the hypothesis sometimes it's a little bit tricky to come up with. So, in order for a hypothesis to be valid, there must be 2 conditions that needs to be met. A valid hypothesis must be testable, and it must be falsifiable. So that means you must be able to run some kind of experiment to test the hypothesis, and it must be potentially wrong. Okay, so you cannot come up with a hypothesis that is never wrong, and I'll show you some examples of that. Now, because of these 2 criteria, the hypothesis will not involve things that allows us to test for opinions, right? Cultural, religious beliefs, superstitions, myth, values, moral judgment, supernaturals. These are not testable things. Okay, these are not things that we can do an experiment and see whether they exist or not. Okay, um, these must not be included in hypothesis. So here are some examples of invalid hypotheses. Animal testing is bad. Now that might be true, that might not be true, depending on who you ask, depending on your opinion. And like I said, because it's an opinion, you are not going to be able to test it. And there's no right or wrong. Everybody is entitled to their own opinion, right? So that's a bad hypothesis. Next one, rock music is better than classical music. Again, that's an opinion. You cannot test an opinion. The garden varies make some plants taller than others. That is superstitious, and in fact, this is not falsifiable. Right? How do I know garden fairies exist or not exist? Right? You might argue that they don't exist because you haven't seen one, but just because you haven't seen one doesn't mean that they don't exist. For example, I haven't seen a dinosaur before, but that doesn't mean that they didn't exist, right? So there's no way to disprove, right, this statement, and so it's not falsifiable, and therefore it's an invalid hypothesis. And the next one is also not falsifiable. Everything that occurs is as a result of divine intervention, right? So when you write a hypothesis, you need to keep in mind to make sure that they are testable and they could potentially be false. Here are some good hypotheses. Plants receiving more sunlight grows taller. Right? You can definitely test that, and that could definitely be wrong. Driving with the windows down will increase fuel consumption. Taking melatonin will increase sleep duration. So all these things are testable and potentially wrong, and that's what makes them good, valid hypotheses. Let's go through a specific example here, right? Observations, asking questions, and writing hypothesis. Right? Let's just recap what we talked about so far. Discovery science uses the observation. Sometimes is qualitative, sometimes is quantitative, and when we are going to be asking questions about those observations, and to find an answer for those questions, we use the scientific method. Right? And when we do that, this is called hypothesis-driven science. So in this example, right, we have two plants in the house, and you notice one is taller than the other. Right? That's an observation. The question is, why is this thing growing taller than the other? Right? They appear to be the same plant here, so what's going on? Right? That's your question. So we are going to have to form a hypothesis, and then we're going to go have to test that out. So to design an experiment to test your hypothesis, we need to consider many variables. Okay, so something that can change in an experiment is called a variable. Okay, so when we do an experiment, we try to keep all the variables standardized, right, the same, except for two. Okay, we try to keep everything standardized, everything the same, right, unchanged, right, or constant, right, except for two variables, right, the dependent variable and the independent variable. So let's take a look at what they are. In an experiment, the independent variable is the condition that is going to be deliberately changed by the person who's conducting the experiment. Right? We change this condition to observe how it is going to affect an other variable. Okay, and that other variable is the dependent variable. Right? So by changing the independent variable, we want to measure, observe, and study any potential effects on the dependent variable. So this is the one that you change, that you have control over. Right? You can control. Okay, you can change. You can control or change as the person who is doing the experiment. This one, the dependent variable, is the one that you don't change, you don't touch. Okay, you observe. Okay, you see if there is any changes happening to the dependent variable because of what you've done to the independent variable. So back to our example, right? You saw the plants. One was tall, one was small. Right? The question is, why is it like that? Logical hypothesis, a valid hypothesis that are testable and falsifiable would be some plants are taller because they received more sunlight, okay, more light. Okay, so to test this hypothesis, we're going to come up with an experiment. So in this experiment, we are going to have two plants, same plants, and one of them is going to be exposed to light for 6 hours per day, and then the other one is going to be exposed to light 12 hours per day. Let's go to our study guide and try some examples. So in question number 6 here, we have several scenarios, and we're going to have to identify which one is the independent variable and which one is the dependent variable. So go ahead and give it a try first before you watch the video, and so you can check your answers later. Student watch a cartoon either alone or with others and then rate how funny they found the cartoon to be. So here the independent variable, the one that you are going to be changing, would be whether they watch the cartoon alone or with others. Okay? So you can put that in here. I'm just going to stick with highlight. It's a little bit quicker over here. And then the dependent variable would be the rating of how funny they found the video. Okay, how funny they found the video. Next, comprehension test was given to students after they had studied textbook material either in silence or with television on. So the independent variable is going to be whether they study in silence or with television on. Right? And the dependent variable would be the test results. So this one I have to write down because it's not part of a sentence. So test results, right, for the comprehension test. Some elementary school teachers were told that a child's parents were college graduates, and other teachers were told that the child's parents had not finished high school. They then rated the child's academic potential. So the dependent variables would be the child's academic potential rating, okay, the ratings, and the independent variable would be whether they were told the child's parents were college graduates or not. Okay. Next one. Students at universities were split into two groups, and each had received different texts for philosophy courses. So traditional textbook or interactive textbook, that's going to be your independent variable, and the final exam marks, that would be the dependent variable. Okay. So hopefully after these examples you have a better understanding of what independent variables and dependent variables are. Remember, in conducting an experiment, we want to keep everything standardized except for the dependent and the independent variables. So here are some examples of what standardized variables are. For example, you want to be using the same type of plants. Okay, if we use one plant that grows fast, the other grows slow, different species of plants, then obviously one is going to be taller than the other, right? We want plants that have the same initial height, right? We want them to be in the same soil. We're going to give them the same amount of water. We want to perhaps control the type of light exposure, right? We want to either expose them both to sunlight, right? Or in this case, because we're trying to expose one to 12 hours of sunlight, it might be harder to control that way. So maybe we want to use like an indoor plant light, right? Humidity, temperature, right? So we want to fix all these things, standardize all these variables, keep them constant, so that we know when we see a different height in the end, the reason for it is because of the single variable that we changed. In this case, the amount of light. So we make a prediction, right? This is part of deductive reasoning. If the hypothesis is correct, then the plant exposed to more light will be taller. And if the hypothesis is not correct, then the plants should be of similar height, or the plant exposed to more light will be shorter. Right? So it's important to predict results of what it looks like if your hypothesis is correct or incorrect. So you would then go ahead and do the experiment, right? You put the plans side by side, basically, right? You might cover up one plan after exposing it to 6 hours of light, and then the other one you would cover up, after 12 hours of light exposure. So here is an example of what the results might look like, right? So the amount of light, 6-hour plan, 12-hour plans, both initially at 12 centimeters. So after 7 days of this experiment, right, you measure the new height, right, and the one that was 6 hours is 13 centimeter, the other 18 centimeter. You can see more light result in more growth in height. So of course this is a very simplified version, right? In a real experiments, we don't base our conclusion off a single trial. We have to repeat this with a large sample size. The larger the sample size, the more accurate your result is. But this is just for demonstration purposes. So the conclusion based on our experimental data is that it supported our hypothesis of more light will creating a taller plant. So where do we go from here? And again, in real life experiments, typically we don't just end with one experiment. The results of one experiment often will create more questions that leads to the start of the next experiment. So in this case, for example, would be what is the optimal amount of light exposure that will result in the tallest plant, right? So you might want to try this again, but then have a wide range of exposure time, right? From 0 hours no sunlight all the way to 24-hour sunlight, right? And then maybe you can take a look at the plants, see which one resulted in the tallest growth, right? And for example, in a drug trial, right, after you have results that show that the drug works, right, in one group and not the other, then you might want to determine the optimal dose, right? That creates the optimal effect, right? So one thing always leads to another in a real experiment. So who came up with this scientific method process, right? There must be someone who invented this, right? And you're absolutely right. There was someone who did this. Before we go into that, let's take a look at this concept of what's called spontaneous generation. So prior to the mid to late 19th century, the origin of microorganisms in decaying matter was in question. People observed that if you leave a piece of meat outside on a hot summer day, for example, come back to it a couple of days later, you will see that the meat would be putrefied, and there would be maggots and flies buzzing around, crawling on it, and whatnot, right? So where do they come from, right? So the concept of spontaneous generation is the fact that living things can grow and be created from non-living things. Okay, so in this case, the living thing would be like the flies and the maggots, and the non-living thing would be the piece of meat. Okay, so when it comes to microorganisms, right, bacteria, fungus, and all that stuff, it's the same kind of argument. Some supported that microbes will only arise from other microbes that perhaps have landed on the food from the air, but other people supported the theory of spontaneous generations, right? Which again, as I told you, states that living things, life, right, practically arises from non-living matter. So who's right? Well, in 1600s, there is this person named Francesco Redi. He wanted to test the hypothesis of spontaneous generation. Right? So he used a process that involves making observations, asking questions, formulating a hypothesis, and designing experiments. Right. So at the time, it was not known as the scientific method yet. It's just like a process that he used to test things, and later on, it became the standard methods of conducting experiments. So what did he do? Well, the observation again is that flies and maggots can be seen around pieces of meat left out on the counter or outside or wherever, right? And the question is, where do flies come from? Is the rotting meat transformed into flies? Right? So that was the question he tried to answer. Hypothesis. Right? Rady's hypothesis was this: only flies can make flies. Rotting meat cannot be transformed into flies. So that's a testable hypothesis that is also potentially falsifiable. So this is what he did, right? So he had open jars. He put some meat in it, right? In open jars, and he did not cover the jars. He then have the same meat put into some jars that has been tightly sealed, and then he had a third groups where there are jars with cloth netting on top, so the flies cannot go in, but they can still smell the meat, for example. So that's the experimental setup, and here the standardized variables would be meat, right? The exposure to flies, right? And presumably how much meat he used and the type of meat he used, and the independent variable in this case would be the type of jars, right? Are they open jars, sealed jars, or covered with a cloth netting, right? And the dependent variables would be will you see flies, right? Presence of flies and maggots, right, on the meat, right? So as expected, right, you see a bunch of flies and maggots going into the open jars, right? And the tightly sealed jars have nothing. I mean, the meat is turning bad, but there's no maggots on it. And finally, with the jar covered with cloth nettings, you see the maggots crawling on the cloth, but not on the meat. Right? So based on this result, he was able to conclude that the flies, only flies make flies, and the meat cannot transform into flies. Unfortunately, Rady's experiment did not convince everybody. Some argue that while spontaneous generation, that living things comes from non-living things, might not apply to larger organisms like maggots and flies, it might still be true to some smaller microbes. So this question was finally answered definitively in late 1800s by Louis Pasteur. Right? So you might recognize this last name, right? Pasteurization, like our milk, right? He's also the guy who invented that. So Louis Pasteur had a hypothesis, right? Pre-existing microorganisms present in air contaminate nutrient broths. Okay, so these are some broths full of nutrients that are perfect for microorganisms to grow. And he predicted that if the broth is sterile, right, if you killed everything in it by heating it up first, then the broth will remain sterile if you don't let new microorganisms go into it. Okay, so what he did was he heat up the broth, and the broth is now considered as sterile, and he has two flasks. Okay? He has a flask where it has a swan neck tubings, so microorganisms in the air will only be able to go in through here, and then they will be trapped here. They won't be able to travel upwards and into the broth. And then he has a flask that has a broken swan neck, so everything in the air is able to go into the broth, right? And then he observed the presence of microorganisms after certain times, and he detected nothing in the sterile broth here. And then with the ones with the broken neck, he was able to detect the microorganisms. So that concluded that definitively that only microorganisms can give rise to other microorganisms, and if it's sterile and there's no pre-existing life form in there, then it's going to remain as such. So that definitively disproved the idea of spontaneous generation.